There are a couple I need later on, the statements, we'll see. Okay, so let me just recall a few things. So exponential map and the adjoint were the important things. Put it over here. So x was Tx at 1, where phi x was a homomorphism. This derivative of x. Most important property is that it commutes with homomorphism. So then phi x was x d phi x. So we may have seen this in the exercises, how useful that is. Maybe another property was that if H and G is a Lie subgroup, then the Lie algebra can be characterized as those x and g such that x per px lies in H, say for t less than some epsilon. That's a nice way to characterize a Lie subalgebra. So that was the exponential map. And the other important concept was the adjoint. Which was given by the derivative of the homomorphism, which is conjugation. So properties that we saw that D of the, so the adjoint itself, I can regard as a homomorphism from G into, say, the endomorphisms, or into the general linear group of G. So this was a D group homomorphism, right? And the derivative of at was little at. And the little at x was a B bracket with x, which was a Lie algebra homomorphism. Most important properties are that at commutes with the exponential map in the following sense. This is the exponential map in the general linear group, and this is in the group. So it's just essentially this property here. And the other one was that G, what is it? It commutes with the conjugation. Yes. So x of at gx is equal to g x g inverse. Again, essentially this property right here for the conjugation automorphism. Okay. Maybe the last one was the kernel of the adjoint is the center of G. Okay, so these are important properties. Exponential map and adjoint. Did you use this one already in the exercises? On Friday, did you use these properties of the adjoint? No? Yes? For example, one thing I'm going to use frequently is, say, as an example, say H and G connected, and H is normal in G, if and only if H is an ideal in G. So, okay, that's an important application, for example. And you can see how powerful these are when you do all these exercises. They're amazing. Okay. Oh, by the way, now on Friday, so I want to make up the 2 lectures that we missed last week, so I can cover enough material. So one suggestion is that 2 of the Fridays where we do exercises, we replace them with a lecture, and then the week after we do exercise again. From when to when were the exercises again? In what room? The problem sessions? They were where and at what time? The problem sessions on Friday, what time were they?
It's Friday's vacation. Do you want to do the exercise this Friday?
No, I want so 2 weeks or 2 lectures I want to make up from last week on a Friday. So 2 of the Fridays where we usually do problems, I want to have a lecture. So one idea is we do it this Friday, if people can make it. But what time were the problem sessions and where? 1:30? At 1:30? 2, 3, do you remember where?
This Friday is a holiday here.
Ah, okay, certainly not then. Next week.
359.
Pardon?
349.
359. 459.
349.
359. Okay, this will be Friday, April, whatever.
How about we begin at 1 o'clock? Is that
Fine with me.
because I have a Romanian geometry course. The professor always at the class at 2.
He starts the class at 2?
Yes, so I only have half an hour.
Ah,
But if it begins at 1, I have 1 hour.
is that okay? Anyone cannot make it at 1? It's okay? So 1 to 2:30? I have to find the room then, whether that's free or not. Okay. So that's April next week, Friday next week. There's no holiday then, I assume. Okay. Okay. 2 more basic concepts. Fundamentals. One is an automorphism. General properties of automorphisms and also derivations. So you can kind of guess what an automorphism is. If it's a linear map and a Lie algebra homomorphism. Little exercise, very simple, is that this implies that the inverse, since it exists, is also an automorphism. So if A respects Lie bracket, the inverse of physics also expects Lie brackets. So that's, of course, what I would mean by an automorphism. And a linear map from G to G is a derivation. If so, it satisfies a usual derivation property. Or if you want, you can also write it as, say, L composed with at x is at Lx plus at x composed with L. Right. So that's equivalent, of course. So that's a derivation, that's an automorphism. And let's make some general comments about them. Maybe first notice let's give this the set of all such things a name. So out G is a set of all automorphisms. Of the Lie algebra. So notice that out G sits inside GLG. It's an isomorphism. It's certainly closed because it's defined by an equation. Anything, so here, of course, it's defined by the automorphism equation. and therefore it's closed. And certainly a subgroup, right? Compositions like automorphisms, so it's a least Lie group. So notice, for example, that then the adjoint over there, so at goes from G into out G. That is a derivative of a conjugation, which is an automorphism, it's automorphism, so it actually goes into out G and GLG. And I think one of the exercises was to show that ad is smooth. And hence a Lie group automorphism. And so ad is Lie group homomorphism with kernel the center. Right. That's useful. But the image is not everything, so a little bit later today we'll come back to what does the image in here look like. They don't all look like that. Okay, so relationship between automorphisms and derivation. It's kind of the way these relationships usually are. So kind of a general principle, all of mathematics, if you have something that respects the Lie structure, then if I differentiate, I get a derivation. So there's an obvious relationship. So you might guess that if I look at this Lie group, right here, out G is a Lie group, this should be the Lie algebra. So. So for derivations, I guess I want to use German der for the algebra. So a set of R, which is a derivation. So the proof is kind of one direction is what I just said. In the other direction, I have to think about it a little bit. So if I take a path, right, so A of t is a path inside out G. With A at 0 is identity. Then I claim that the derivative is a derivation. So for this, I just differentiate the automorphism equation. Right, and then use the product rule. Right? If I differentiate, I get precisely this equation right here for the derivative. So that's one direction. We want to use this property of a Lie subalgebra in the other direction. Right, so this here, so what does this direction prove? It proves that I guess it proves this direction, this inclusion. I have a curve inside H, derivative lies in the Lie algebra. Now we have to prove the converse. So let's do the following. So I want to take a derivation. And I want to prove it's a derivative of an automorphism. So what do you think the automorphism should be? Again, a general kind of principle. To go from here to here, you take a derivative. To go from a derivation to an automorphism, there's something natural one can do. In fact, this suggests what you should do, right? To construct the automorphism, this here would be out G, right? To construct the automorphism, I want to take the exponential. Right? Exponential, but now we're in a subgroup of the general linear group. In the general linear group, the exponential is a usual matrix exponential. So I want to show that this is an automorphism for RT. So that's the statement over there. So that would prove this direction. Right? I take a derivation, then e to the tx is an automorphism. Then I'm done. Okay. So here I differentiate again, but now I have to differentiate for all. So for all t. So let's look at as follows. So what's the trick? I take e to the TL or minus TL minus t. Apply to e to the TLA, e to the TLB, and differentiate. Or in other words, I want to show, okay, here's what I want to show. That this is, well, we usually use x and y for x and the algebra, doesn't matter, that this is xy for RT. If I bring et to t on the other side, that's the automorphism equation, right? So that's the trick. Show that this curve is constant in t. And of course, for that, you differentiate. So take ddt on the left-hand side. Show that it will be 0. Then it will be constant. And clearly, when t is 0, these are all the entities, so I get xy. Right? So that will be the proof. So I use a product rule. Remember how to differentiate e to the TL in general. What is that? So I'm using L here. L times e to the TL, but also e to the TL times L. So they commute. How do you prove that?
By definition of exponential.
So this is a power series, right? Out of the power series, differentiate term by term, which you can do because it's absolutely convergent, multiply by L, and that's how you get it. And of course, then since the powers of L commute with L, I don't matter on which side I put it. So here I can choose where I put L. I put it on different sides in the different terms. So I use a product rule here, so I get minus e to the minus TLL, e to the TLX. Let's maybe give these things a name. Let's call V e to the TLX and W e to the TLY. So I differentiate. Here I just take e to the TL again. So e to the TLX is called V. E to the TLY is called W. Plus this here, so e to the minus TL. Differentiate inside. Here again I can decide where to put it. I put it before this time. And it becomes L times e to the TLX. E to the TLX was V. The other term is W. And do it the other way around. VLW. If I differentiate this one, put L in front of it. So now cancel e to the TL. Oh, sorry, not cancel that. Put it in front of it. Times minus LVW plus LVW plus VLW. And the derivation equation says that this is 0. Okay. So L times this is this plus this. This is true for all t, of course. I took the derivative at any point t. So derivative 0, it's a constant curve. It starts with this one, so that's it. And this is the automorphism equation. So that's kind of this usual thing. My goal is this. From automorphism derivation, I differentiate from derivation to automorphism. I take the exponential And one usually has to make sense out of what one means by exponential depending on the context this arises. Like here it's very easy. I just take the exponential of the D group. Okay, so automorphisms, Lie algebra derivations. And yeah, if I said that, say a simple kind of derivation. So notice that if I take x in the Lie algebra, then add x from G to G is a derivation. So I claim that, let's look at it like this here. So what does it say? Add x, add y. So replace x by y here. Is that how I want to do it? Is adjoint of xy plus add x. I did something wrong. Replace x by y plus add y add x. Sorry. So that's the derivation property, right? I have to show that. But of course, just looking at this, this says that adjoint of xy is add x, add y minus add y, add x. And that's the Lie bracket being add x and add y in the general linear algebra. Right, and we know that, right? That was an automorphism. So if you wanted, this was the Jacob identity. So in fact, they're equivalent. So this is derivation if and only if the Jacob identity is satisfied. So you have natural derivations inside the Lie algebra of all derivations. And we give those a name. So the definition is L in derivation of G is an inner derivation. If it's of that form, so L is equal to add x for some x in G. So the special derivations are very important. They're called inner derivations. And then I can also define inner automorphism. So now it's not so easy to find by an equation, but I use the same kind of rigmarole we had here, right? Lie automorphism was a derivation. Have a derivation, I take e to the t times the derivation to get an automorphism. Right? So here I can say G is inner. Well, let's if the following. So let me do it the other way around. In G is the connected Lie subgroup of out G with Lie algebra. The inner derivations. Sorry, with Lie algebra with inner derivations. Yes, for this to make sense, I have to observe that that in G inside derivation G, is a subalgebra. In fact, it's better than that. Let's see what's it's another equation I can write down for derivations. So let's take L a derivation. So write down the equation and we'll see when we're talking. Let's take a derivation and let's take compared with ADX. So I claim L ADX is equal to, you can imagine how they should be related. What should that be? Well, what can I do? I can just put the L down here. I claim it's at Lx. I just crank it out, apply to Ly. This is L, well, so this is a commutator, so I have to show L composed with ADX minus ADX composed with L is at Lx. Applied to an element, so it says L applied to xy minus x ly is equal to lxy. Right, and that's just the automorphism property. Put it, sorry, the derivation property. Put it on the other side. Right. So this is true since L is a derivation. So what does it say? It says that, in fact, it says more than what I wanted. Right now, it says that if I take any derivation, take a Lie bracket with what I called, what I called int g. That's contained in int g. Right, that's what this says here. Take a derivation, take a bracket with something that's inner. Inner ones were precisely ADX. Derivations are precisely ADX. And that's again, is again inner. So it says this here. Derivation bracket with inner is inner. So I actually proved more than it's a subalgebra. Right? So I proved here the, maybe it's called a proposition. Int g is an ideal in out g, in derivation g. So not only is it a subalgebra, it's even an ideal. Okay. Where did I? Oh, here I did the definition. Okay. So that's the relationship between the Lie algebras, between int g and derivation g. That should, of course, then give me a relationship between the groups. So another consequence is then int g is a normal subgroup of out g. So let's see what we have to prove.
Using the same notation from Luigi.
Pardon?
Using the same notation from the Lie group and the.
Oh no, I don't. I'm confusing things, right? That's not what I mean.
It's very nice, but
Pardon?
you are using the same notation for the Lie group and the algebra.
I should not do that, of course.
For the
The
integration.
inner derivation is the inner automorphism.
Ah. So what did I call the Lie group of int? No, what
You put there
is this one is wrong, right?
group.
No? Oh, int. Derivations. No. What did I prove here? Isn't I doing what? Now you confuse me. Because something is wrong. Int G was a Lie subgroup. Derivations were the inner derivations, and der G is a normal subgroup. Or didn't give the inner derivations a name, is that it?
The algebra is rather a little different, but the notation is almost the same.
For which groups? For int.
Here,
Okay, okay. Of course, this here denotes a Lie subgroup. I think on the blackboard I may have trouble distinguishing int and German int, so let's me call it Lie algebra of int. So what did we prove? Here we proved the Lie algebra is an ideal. Is an ideal in derivations.
and there is the algebra too.
So here should be Lie algebra again, right? Which by definitions are the inner ones. So this is a set of all adx. Okay. And so that's a set of all adx's are normal. Okay. Now it makes more sense, I think, right? Is this proposition right now? Okay, the Lie algebra automorphisms were the derivations, right? This was one of the previous things, and the Lie algebra of int G is by definition the inner derivations. So this is now simply true because since the Lie algebra of int is an ideal in the Lie algebra in the derivations. That's what we proved over there. Okay. So we have a sequence of Lie groups, and we summarize this over here. We have int G contained in the automorphisms of G contained in GLG. Right, that's a sequence of Lie subgroups now with corresponding Lie algebras. So let me again denote this on the blackboard by Lie int containing derivations of G contained in the Lie algebra of GLG. And this here was a normal subgroup. If I have a normal subgroup, I can take the quotient, that's again a group. So color here I get out G mod int G is a Lie group with a Lie algebra. Derivations G mod the Lie algebra, so inner derivations. So we're going to write it as mod Rx. Okay. So the way to write int G, the inner automorphism, is kind of not so convenient right here. So what does it say? It says int G is the unique connected Lie subgroup of out G with Lie algebra derivations. Right? That's not such a nice definition. There's some different ways of looking at this. So on the one hand, I can say, what does this mean? It says that out G, int G is generated by e to the odd x, by a set of e to the odd x. So why is that? Odd x are the inner ones, right? That's the definition. So I take an exponential of an inner one, an exponential of Lie algebra. I get something legal, of course, right? But what do we have to add to say this generates the whole thing? Just have to add a word or a lemma.
This is connected, is generated by error code of the entity.
Right, so this here, X is a local diffeomorphism, right? This generates an neighborhood entity. So this contains a neighborhood of the identity. And Lemma said that the neighborhood entity generates everything. Interesting question is whether int G is, with ever elegant int G's of the form e to the odd x for some x or not. So I could look at the exponential map. Which goes from a set of derivations, right? So inner derivations into int G. And is this onto? Is the question. Right? Can I write every inner one of the form e to the odd x here? This here takes an odd x to e to the odd x. So is that onto? Right. I think you saw in the exercises that this is not always true. Exponential maps are not always onto. Did you do that exercise? For G and R, it wasn't onto? No? Well, so maybe let's think about that a little bit just to give you a hint. If I look at something of the form e to the TA, so that's an exponential of a matrix. What special property does that have that not all matrices have? Say A is real. I think once was supposed to, there was a difference between real and complexes in the exercise, right? What about the eigenvalues of this thing? Or the eigenvalues of e to the TA? Or just e to the a, right? Doesn't matter what t is. But I can't see what the eigenvalues of e to the a. Can
I saw an exercise that said This matrix has a square root.
Has a square root, yes. There's a good. Well, okay, that's a good way to look at it. What's the square root? What's the square root?
Nice abstraction.
Yes, what's the square root of this matrix? You can just write it down. Think of e to the TA. That's a homomorphism, right? So I can easily take the square root. What's the square root?
T equals root 1 half.
So it has a square root, absolutely. Not every matrix has a square root. Okay. For example, eigenvalues are positive, okay, equal to 0. Right? So things that are of e to the a of something have special properties. Because you can see the difference between real and complex, right? For complex ones, matrices you can take a square root. For real ones, you can't. So it's a subtle question of when it's onto and when it's not. Sometimes it's, sometimes it's not. And here I think it is, but I don't remember. So exercise, show it's onto. In all the important examples it's onto, but in this generality I forget right now. But I can view it in a different way, which is useful. I can view int g is isomorphic to g mod the center of g. And the automorphism goes from g to at g. Why does it go to int g? So why is this an element in int g? So they're both Lie groups, right? If I could show that that's true, well, let's see, I probably need to assume G connected. They're both connected Lie groups, right? This is connected, this is connected. So I can show they agree in neighborhood identity. If I can show they agree in neighborhood identity, I'm done. So let's take something, an element G that lies in neighborhood identity. Let's write it as x vex. This was e to the x, right? Well, that by definition lies in int G. That's what we said over there also. So hence they agree in neighborhood identity. And hints are the same. They're generated by the neighborhood identity and they're connected. So clear need connected there. So that shows it goes into that group. Well, so we also know that G goes to at G is a homomorphism. Right, so this is here a homomorphism of Lie groups. And now I just have, and what do I have to say? maybe let's just say like this. I look at the map from, I now have a homomorphism from G to int G. This after was in out G, so I have a homomorphism like this. G goes to out G. And this homomorphism is onto. That's what this is if you want to. This homomorphism is onto. And the kernel is this kernel in the center of G. So now it reduces to an exercise, right? When you homomorphism with a certain kernel, which is onto, then the image is isomorphic to the group moderate center. This is one of the exercises. So, okay, so that's, I should start this. You start with this here, right? This is, we show that this is true, that it lies in int G. And we know it's a homomorphism already, and it's onto has kernel the center. So all these things we know. So this is actually a nice way to look at it. It's just the set of all adjoints of Lie group's elements. It's a much better way to view it. Of course, notice that the left-hand side here I define by without knowing a Lie group, right? With a set of inner derivations. It's a set of, and for this I don't need a Lie group that's associated to that. Right? This is just a Lie algebra concept. Here I have a Lie group, but of course we know for every Lie algebra there exists a Lie group. Right? So, the best way to look at this, if you want to, is given the Lie algebra G, choose your unique connected Lie group with Lie algebra G, and then apply that to that Lie group. So I can always use that by choosing the Lie group G for that Lie algebra in order to work with it or in order to prove things about it. Anything else I want to say? Okay. Last concept before I go on to the last topic is the killing form. So connected to other morphisms is the killing form of Lie algebra G. That's on a very simple, basic object associated to Lie algebra, which is sometimes very important. So I just define this as follows. It's a bilinear form. Let's call it B. X, Y goes to the trace of other X composed with other Y. So take a trace of the at homomorphism, and I get something Lie algebra valued, and its properties are that B is a symmetric bilinear form. That's clear, right? Certainly trace AB is trace BA, so it's symmetric. You multiply X by a constant, it just comes out. So that property is obvious. B restricts automorphisms. So automorphisms are symmetries of the killing form. Unfortunately, that's not always a metric, so it's not quite as useful as you might think, although sometimes it is. We have a derivation, of course, that we just differentiate. If L is a derivation. Just differentiate this equation, right? Maybe the last property is that this is not non-degenerate, it has a certain kernel, and the kernel of B is just the what's the kernel of B again? Well, the kernel of B is not so easy to describe, but at least the kernel of B is an ideal. In G. So I'll remind you, what's the kernel of a bilinear form? How's it defined? So in general, for a bilinear form, what do I mean by the kernel of the bilinear form?
X in G such that B X Y 0 for all y.
Yes. So all vectors x where that inner part with everything is 0, that's a kernel. Right? So that makes it it's not degenerate if and only if the kernel is 0, right? So if it has a kernel, it's not non-degenerate, and then it's less useful. Okay. In fact, for lots of Lie algebras, the killing form is 0, just vanishes. So sometimes it doesn't give you any information. In fact, an interesting problem to characterize those Lie algebras where the killing form is 0. That's not so easy. What Lie algebras have this property, killing form is 0? I don't remember if there's a good characterization of it. So one thing that we'll see easily later on, nilpotent Lie algebras have this property, killing form is 0. But not all of them. Not all Lie algebras with killing form 0 are nilpotent. So we'll come back to that later. But they're solvable. They're all solvable. And anyway. But for example, if the Lie algebra has no ideals, then either B is 0 or B is not degenerate. Right, so because you have either. Okay. So what do we have to prove? Well, why is B true? I guess A was clear. Why is B true? So I have to prove trace of at Lx, at Ly is trace of at x at y. Remember what at Lx was? Let's discuss that earlier. That was, did we discuss that? That's just because L is an automorphism. In fact, that is if and only if. So if you just crank it out, I think we did this earlier, it just says L is an automorphism. It's equivalent to that. So of course now the left-hand side, I just use this trace of L at x, L inverse, L at y, L inverse. So these three cancel. And L, a matrix, L inverse has the same trace. Okay. Differentiating, I get this property for derivations. And the last one is also easy if I write it down. It's supposed to be an ideal. Sorry, it's supposed to be, kernel is supposed to be an ideal. So what does that mean? So I have kernel B contained in G. So it means that if X is in the kernel, I need to show that X, Y is in the kernel for all Y. Right, that's what needs to be ideal. D brackets of this with this lies in here. So X lies in the kernel, so Bxy is 0 for all Y. That's what this means. And now I need to show that the Lie bracket also lies in the kernel. This is 0 for all Z. That means what it means for this vector to lie in the kernel. But what can I do here? Right, so here I could use, so how can I view this derivation property? I can, where is it? Here it's this one, right? That derivation is just Q-symmetric if you want to, right? It's like it's Q-symmetric for this linear form. And of course, when we use add x or add y, I want to put something on the other side. And put x on the other side. So add y is a derivation. It's an inner one. So this is equal to minus b add y, flip these two. Wait, is that all right? Ah, yes. So this lies in the kernel, right? My assumption. Something lies in the kernel, it's 0 with everything. So it's 0 with that. Okay. So that's how I want to use this kind of property here. Often I want that add x is Q-symmetric. So Lie bracket, I can always switch around two things and pay by a minus sign. That's how I want to look at it, right? That's extremely useful to use that property B over there. Okay, so corollary. If G has no ideals, this implies that B is not degenerate. Or B is 0. But we're going to see that later on we can take this away. So if the killing form is 0, it actually G can't have no ideals. Which is not quite obvious right now. But anyway, so this, that's one of the usefulness of the killing form, that later on we classify Lie out as no ideals, and the technique we're going to use is that B is a non-degenerate bilinear form on this Lie algebra. So we can do a little bit of geometry. Okay. Last concept is complexification. And then I do lots of examples. So, because this is something you always do in linear algebra, right? When you want to prove something in linear algebra, you complexify, because complex linear algebra is so much simpler than real linear algebra. And sometimes the hard part is to reinterpret, well, if I proved something in the complex case, what does that mean for the underlying real matrix? Right? So we do the same thing for Lie algebras. So if G is real, then G tends to C is a complex Lie algebra. By declaring the Lie bracket kind of the obvious way, I think that's an element of the complexification, right? A and B are in the real Lie algebra. A plus IB is by definition an element in the complex Lie algebra, and just make it bilinear. So AB minus CD minus BD AC. Real ones minus the complex ones plus I times the rest. AD plus BC. Okay. So that becomes a complex Lie algebra. That's easy to check. So for example, if I take GLNR, its complexification is, by definition, if you want to, the same thing as GLNC. GLNC is A plus IB, A and B are real matrices. So GLNC is a complexification. Or similar for all the other ones that are easily defined. SL and C complexification is isomorphic to SL and R. It's isomorphic to SL and C. In fact, this here is a nice fact that has all kinds of implications. So to go backwards is not so obvious, right? If I take a complex D algebra, can I write it as a complexification of a real one or not? So we'll say G is complex. So definition again. Then H is a real form of a complex D algebra G if H tends to C is isomorphic to G. So all the complexifications of linear D algebras, that's a set of complex D algebras, and H is then called a real form of the D algebra G. Or equivalently, H contained in G is a real D subalgebra with G is a set of all A plus IB where A and B lie in H. So certainly in one direction that's clear, right? Here, if that's how we define G tends to C, so this has a subalgebra G. G is contained in G and C certainly. And G tends to C. It's a subalgebra in the real sense. It's a real subalgebra. And A plus IB is the whole algebra. Okay. And of course, now if I have an H which satisfies this here, then H is contained in here, which is contained in here by isomorphism, then the same thing holds. Right? So these are two different ways of viewing that something has a real form. Now, a comment here that we're going to see later on, a complex D algebra has many real forms. So to go backwards is not unique, right? Because forwards, it's a natural, simple process. I go from real to complex. I go from complex to real is tricky. And say classifying, for example, given a complex D algebra, what are all the possible real forms of the complex D algebra? That can be very tricky. It's a non-trivial problem. And later on, we're going to have to face this problem. For example, one thing we're going to do is I want to classify all compact Lie groups. I go to the Lie algebra, I complexify the compact ones, then I have to learn how to go backwards. Because going backwards is a hard part. And what's worse is that going backwards, I have to be careful. If I take a compact Lie group, I take its Lie to complexify. If I now take a real form of it, it doesn't have to be compact. So it has compact real forms, it has non-compact real forms, and this situation is a little complicated. So that's an interesting question. What else do you want to say about this? Well, maybe before I do make the last comment about this, let me look at an example, an application of this. So I claim as an application, I can prove that, the following. If I look at SL and R, so that's my Lie group, say, and I look at the universal cover, G tilde, then I claim there exists no homomorphism, no one-to-one homomorphism. So let's call it phi from G tilde into GLNR or GLNC. So in other words, it's not a subalgebra, it's not a matrix algebra. Right? So this group SLNR is never contained in the, I can never represent them by matrices, real or complex, doesn't matter. So I promised that earlier on. Of course, for this to even make sense, I have to know from something we're going to see next week that the group is not simply connected. Otherwise, we're the same group. Right? Let's accept this for the moment that this is not a simply connected Lie group. And now let's use a concept of complexification to prove that. Okay, so I have my homomorphism phi from G tilde into GLNC. Of course, since GLNR is a subgroup of GLNC, it doesn't matter if I go into GLNR or GLNC, right? So I prove both at the same time. It's a one-to-one homomorphism. Then I get a homomorphism of D algebras, which is SLNC, SLNR. Well, of course, okay, maybe this is a complex Lie group. This is not maybe the real statement would be there's no homomorphisms of real Lie groups from this into this one, which is injective. Of course, I can now go into here and forget that this is a complex Lie group and just regard this as a homomorphism. So then G, this derivative goes from there to there. Well, maybe it's better to use this into GLNR. Otherwise, it's going to get confusing. Let's just use this as into GLNR. It's actually is equivalent in the end, so let's go into GLNR. It'll be simpler. So I can complexify. From G tilde tends to C into GLNR tends to C. What's G tilde tends to C? Well, this is SLNR. Right? So complexifying I get SLNC. And this complexified is GLNC. So this is a Lie algebra homomorphism. So now I have a Lie algebra homomorphism, and now I can do the following. I can integrate it. So now I need the other property we're going to see next week, so later. Phi 1 of SLNC is 0. So it's kind of funny, right? SLNR is not simply connect, but SLNC is. So curve or real matrices of determine one, I can homogeneous identity as long as I'm allowed to go through complex ones, but I can't do it if I stay within real ones. So I want to use this fact here, and I want to use this fact over there. So just to show you how complexifications can be so useful. So I have this homomorphism here, which I regard as something from SLNC to GLNC. And now this implies that there exists a psi from SLNC into GLNC with derivative d phi tends to C. But this was one of these things we proved when we talked about covering. For a homomorphism, I get a derivative. For the converse, if I assume that the domain is a simply connected Lie, I can integrate. Right? So here now using that SLNC is simply connected to integrate. I can do it of the reals, I can do it of the complexes. Kind of funny again, right? So Complex are much simpler. Let's put this together now. By drawing a diagram. So I look at SL and R universal cover. That's with my group G, right? I look at the covering map onto SL and R by definition. I have an inclusion here into SL and C. And I just constructed a homomorphism into GL and C. And we assumed we had a homomorphism from SL and R into GL and R, which is a subgroup of GL and C. Sorry. What do we call it? We call it phi, right? That's my phi. Right, we assume there's a one-to-one homomorphism from use a cover of SLNR into GLNR or GLNC. This one is a subgroup of the other. I guess I'm using that again here. But there are different ways to do that. I can first look at the covering, go to SLNR. SLNR sits naturally inside SLNC. And I just constructed this homomorphism where deep C was d phi tensor C. So I claim this diagram is commutative. So I can go this way, and this way. So pi composed with I composed with C. I claim the same thing as phi. Why is that? Yes, since this is true on the Lie algebra level. Right. After all, if I take d phi and complexify, then I got deep C, right? Oh, yeah. And of course, here this covering here is just an isomorphism of the algebras, right? This is an inclusion here, so this inclusion becomes an isomorphism when I complexify. So on the level of Lie algebras, after complexifying, and remember, a homomorphism on Lie groups is determined by the derivative. Right? So if I know that this commutes on the derivative level, then that uniqueness fact implies it also commutes on the homomorphism level itself. Why is that impossible? I claim now I have a contradiction. This cannot be. But, what's the but? This is not possible on the group level. What do you know about phi here? Phi was a supposed embedding, supposed And it was supposed to be one-to-one, right? This was our assumption that does such a thing exist. Can this map be one-to-one? So can this map be one-to-one? It's a composition of these maps. That can't be. Because it's a covering, so it has a kernel. Right, so it can't be a pi kernel of pi. It's non-trivial. Assuming, like we said, that SL and R is not simply connected, so the universal cover really is a different group, right? Then that covering map has a kernel. But if it has a kernel, then this has a kernel, also a contradiction. Okay, it's kind of a nice way to see that this is not a loop. By the way, also we're going to identify these groups later on. It's not the same. It's Z when n is equal to 2, and Z2 when n is bigger than 2. So it's a twofold cover for large n and an infinite cover for n equal to 2. So you can make kind of a general principle of this if you want to. So you get lots of examples as long as you have say a real Lie group which is not simply connected, right? That's what you have to start out with. So you can look at them as a cover. What do I need then? When I complexify, it must be the Lie algebra of a group which is simply connected. Right? What do we use? We use that SL and R was not simply connected. That's my Lie group, right? I take the Lie algebra, complexify, I get SL and C. That's the Lie algebra of a Lie group, SL and C, and I use that is simply connected. So I can integrate the homomorphism. That's what I'm using. So with that, you can construct lots of examples of Lie groups which are not matrix groups. So that's kind of interesting. Okay, I'll prove one or two more facts about complexifications on Thursday, and then I'll start with the examples, lots of examples. Okay. Remember, if you have questions, office hours at any time. If you have problems with the homework, you can come by and ask me.